do that because, all right. So where are we here? Calc 3. Let me move the chat bar over there. Let me move the chat bar over here. Okay. Okay, so Calc 3, fall 2020. And let's look at homework 3 first. All right. And then we're going to do today's stuff. So here, that's the last one. So let me back up. These are all the pages, right? So I took pictures of the pages. This is what's posted. So number 1, it's your just iterated double integrals. You just had to compute it. So 19 minus e to the 6th over 2. If you're into decimal approximations, I think I provided your decimals. So negative 192-ish for that one. Number 2, work from the inside to the outside, integrate the x's, then integrate the y's. I just did that in a few steps. 62 over 21 for your exact answer, 2.9-ish, okay? You can look at these on your own. I'm just going to kind of run through them. All right, number 3, work from the inside to the outside, integrate the y's first, evaluate then the x's. With 2ln2 sine 1, whatever that is, about 1.16-ish, okay? There it is. I'm going quickly through these because the answers are already posted, all right? All right, so the answers are already there, okay? Number 4, work from the inside to the outside. Had to use some integration by parts in the middle here. So I'm trying to show a lot of work so you have all the details there. So just kind of I mean, if you have it and you've got a 25 out of 25, awesome. If you need to see the details, I'm just writing it out so you can just check it out and see. Okay, so e squared plus 4 or 2-ish, okay? Number 5, I used integration by parts here, but I used the table method for that one. So e squared minus 1 for that answer. A lot of numbers here. They're all numbers because you're just computing them, okay? Number 6, another iterated for you to compute, so 256 over 21, okay? Number 7, another one for you to compute, so sine 1, because it's radians, right? Okay, so number 8 is where you had to start setting it up yourself, okay? So I went ahead and did a type 1 here, okay, dy dx, all right? So I went from x cubed to x squared for the inside bounds, 0 to 1 for the outside bounds, 25 over 84 is that answer, okay? Going quickly through these, you can go back through them. They're posted in Canvas, okay? I went ahead and did a dx dy for this one. You could do dy dx, it doesn't matter. If you did dy dx, then this is your integral. But because I did dy dx for that one, I went ahead and did dx dy for this one just to change it up in my solutions, okay? So either way, whether you solve this way or set it up and solve that way, you're going to get this answer, 314-ish, okay? So 314 should be positive. We're finding volumes, so we're not going to have negative numbers, right? So it should be positive. Did you do the fundamental theorem of calculus like the right way? Did you do it the right way? Plug in the top, plug in the bottom. So check that over. All right. Number 10. So I went ahead and cosine 9 is positive. So cosine 9 would be, why would it be negative? Okay, because when you integrate sine, you get negative cosine, right? Did you get that there? When you do the integral of sine, you get negative cosine. Okay, you can check those formulas, but you get negative. Number 10. So I did a type 2 here. So dx, I did a type 1, I guess, when I set it up. All right. Oh, wait a minute. I'm sorry. Number 10 is where you have to switch the variables around. Okay, so they gave you dx, dy, graph the base, and change it to dy, dx like this. Okay, so your bounds, instead of going from y squared to 9, you're going to go 0 to radical x. All right, 1/4 sine 81 is that answer. Okay, so number 11. So number 11 is you got to change the bounds again. So did I do that one? Did I do that one as an example last time? Oh, or did I do that one in the video I made? Maybe I did that one in the video I made. Did you guys even watch the videos I made? You probably didn't need to. Okay, that's a big number though. If you went for the decimal approximation there, you're in the 2 million range. Okay, it's very similar to the one I did in the video. Okay. And then here's number 12. So you're doing polar, and we're going to go over some more polar today, but we should have gone over plenty of polar for you to get through the 2 problems that were on here. Okay, 7/3 plus 7/6 radical 2 for this one. Okay, so change x to r cosine theta, change your y's to r sine theta, and then you change dA to r d theta. So that's how you handle these, okay? And then number 13, change the y to r sine theta, change the dA to r drd theta, and then they're giving you a semicircle here, right? Okay, above the x-axis. So you have the r is the region above the x-axis within the, so it's 0 to 2 for the radius, okay, and then the 0 to pi. All right, so 16 thirds there. Here's your proof. So this is a really cool thing. I mean, you could have probably Googled something. I don't know how much I care, but I wanted you to take a look at this because this relates Fubini's theorem to Clairaint's theorem. Okay, that's what's really cool about this. This is like this is a really big theorem. Fubini's theorem says if you have a continuous function, it doesn't matter if you do dx dy or dy dx. It's not going to matter which way you integrate. So that's if you have a continuous function. And then Clairaint's theorem with partial derivatives says if you have a continuous function, it doesn't matter if you do the partial with respect to x then y or the partial with respect to y then x, and it doesn't matter. And this is like a theorem that they came up with that links the together, which is really cool. So this is a version of the proof of why it works. I'm not going to ask you any proofs on any tests or quizzes or anything like that, but I just wanted to get a tiny little bit more of theory in our life, just a tiny bit more. You're not going to have any more theory in your life. It's all going to be applied and practical. Okay. But this is a theorem that relates the Fubini's, if you have a continuous function, then the order of the integration with your double integrals, and then the order of finding partial derivatives with your double derivatives, with your finding the second partials, it just is something that's really cool how they're related. Okay, so see, that's a proof that I liked. Okay, there's probably about 20 different proofs out there. Okay, so you probably hopefully found something really, but the rest of it is, you got to make sure that you can set these up and compute them. Okay, so I think it froze up on me, but I'm kind of flipping back through the pages. All right, so you just need to make sure you can set these up and compute them. All right, so we are going to, let's go, and then this is already posted for you. Okay, so use it as a study guide or whatever you want to do. This is going backwards. Here we go. This is us today. All right, so today we're going to review rectangular, okay? And then we are going to go back over polar and we're going to review polar. We're going to do an polar example, and I guess we're going to do 2 polar examples. And then we're going to get into center of mass, okay, and do 1 center of mass problem, okay. Then we're going to do surface area, okay, find the surface area of a surface is a double integral application, and we're going to do a few examples of surface area, okay. And then if we have time, I'd like to do a triple integral anyways before you leave, okay. But it's pretty much application day, okay. So what kind of things are you going to use with double integrals? All right, so know how to set them up. So let's go ahead and do, all right, so we're here. Okay, so let's go ahead and start reviewing our stuff. Okay, so let's go ahead and review. All right, get my pencil. You ready? All right, here we go. So write this with me or whatever you guys do. Okay, stay with me, stay on top of this. And so this is from 15.2. I want to do one more of these, and it's a review problem, not necessarily a problem in the book. I found it in another book that's, like what we've been doing. So let's go ahead and do this one. So it's a double integral. It's y over 1 plus x squared. Okay, d is bounded by radical x, y equals radical x, y is 0, and x is 1. Okay, so we want to set up a double integral. So we've got to figure out what our base looks like so we can deal with the bounds, right? So let's go ahead and draw the base. All right, so let's just go ahead and sketch this base right here. All right, can you see it's writing? So there's the y-axis, here's the x-axis. All right, so this is rectangular. So 15.2 is the rectangular, and then 15.3 was polar. So let's kind of do rectangular and then go back and review polar. All right, what do we have for our curves here? We have y equals radical x. Okay, so we've y equals radical x looks like this, right? All right, so y equals radical x. Y equals 0, that's going to be the x-axis. Okay, so y equals 0 is going to be the x-axis. Try to write over it. X equals 1 is a vertical line over here, x equals 1. All right, so this is x equals 1. Y equals 0 is the x-axis, okay? And this is y equals radical x. All right, so this is our kind of our base right here. This is what it is. All right, And so, I mean, we can get points of intersection also. What is this point right here? Well, when x is 1, y is radical 1. So that point is going to be 1, 1. All right. And this is the origin, you can tell. All right. Type 1, type 2. This is pretty much the way they gave us the problems. It's set up to do a type 1, isn't it? Okay. So it's set up to do a type 1. All right. So let's set up our integral. So the integrand is y over 1 plus x squared. Okay. We're going to do a dy dx. We're going to do a type 1. Okay. So what about those inside bounds? Okay. So the inside bounds are going to go from 0 to radical x, right? So 0 to radical x. Okay. So 0 to radical x. 0 to radical x for the inside bounds. Okay. And then what about the x equals the horizontal bounds? Go from 0 to 1. 0 to 1. Do you see it? Okay, so do you see it okay? All right, so here's the setup. All right, and this is critically important. So even when it's time for a quiz and a test, then you have to go solve it, but you got to set it up right? You got to make sure you're setting it up right, okay? Integrate with respect to y first. So whatever x squared is going to be constant, okay? So what do we have when we integrate with respect to y? So the 0 to 1 is going to stay out here. So you're going to have y squared over 2, okay? All right, there's integrate with respect to y, and then just bring along with you the 1 over 1 plus x squared, okay? We're going to evaluate this from 0 to radical x, okay, and then dx, all right? So integrate with respect to y. You're integrating y. The 1 over x squared in the denominator comes over as a constant, okay? So integrate with respect to y, you get y squared over 2. Evaluate. Okay, so you're going to evaluate. So plug in the upper bound. So plug in radical x and square it. You're going to have x over 2 times radical 1 over 1 plus x squared. Okay, minus plug in the lower bound. You're going to have 0. All right, so use substitution. Okay, so let's let u equal the denominator. And then du is what? 2x dx. So du over 2x is a dx substitution. All right. So you rewrite this integral. You have x in the numerator. Okay. So you have the 2 times u in the denominator, and then dx is du over 2x. So, all right. The x's cancel. So you can cancel those x's. All right, so they're gone. Pull out the 1/4 if you want to. Okay, so we can pull out the 1/4, and what do we integrate in here? 1 over u. So we're integrating 1 over u. So it's going to be natural log. So you have 1/4 up front. Natural log absolute value of u, which is 1 plus x squared. Okay, and then we're going to evaluate this from 0 to 1. Those are our x bounds. Okay, so plug in the upper bound, 1/4. Natural log 1 plus 1 is 2. Plug in the lower bound, you have 1/4 natural log of 0. Okay, natural log of 0. I'm sorry, not natural log of 0. Natural log of 1. Okay, natural log of 1 is 0. My head always goes, oh, you know, I always go ahead of myself with that. So 1/4 natural log 2 for your final answer, since the natural log of, so I want this back. Okay, so there's your answer. Okay, so remember doing rectangular? I just thought we would do something like that to get us warmed up. All right, so this is how we kind of started the chapter. We started the chapter doing iterated doubles where they were already set up for us so we can practice the process of integrate the inside, then integrate the outside, okay? You can only integrate with respect to one variable at a time, integrate the inside variable, hold the outside one constant, all right? Then evaluate, then integrate the outside variable, okay? All right, and then we got to a point here, well, you know what? Iterated integrals are nice, but you're going to have to set them up yourselves. So we set them up ourselves, okay? And then we moved on from here. So if you have circular bases, it's so much easier to deal with change into polar, using polar, your polar conversions, right? Instead of rectangular. It's possible to do rectangular, you know? I mean, if you want to integrate from the x-axis to radical, 1 minus x squared. If it's a semicircle, it's fine, but it's just so much easier to change your circles, x squared plus y squared equals 1, so much easier to change it to r squared, okay? So then what happened, this is frozen up. So what happened after we did the rectangular, we moved on to the polar coordinates, right? So we spent a good amount of time at the end of last class talking about this, right? This is the same exact, I just copied and pasted this page in here from last week. So some double integrals are much easier to evaluate in polar than rectangular, okay? So if we have circular regions, circular bases, we look for the opportunity to do in polar instead of in rectangular, okay? Will they always tell you to convert to polar? They won't. You'll see when we do the application problems, we're going to look at it, we're going to figure out how to evaluate the double integral, okay? If you have a lot of x squared plus y squareds, if you have a lot of circular bases in here, then we want to do the conversion to polar. It's just easier, all right? You don't have to, but it's just easier, okay? So polar coordinates are the r theta, right? So you have to do your x equals r cosine theta. You're going to change your y's to r sine theta, okay? We know why, because that's just that's your unit circle trig right here, okay? We know, and I was showing you that over here, just bringing some trig or pre-calculus, wherever you learn this, okay? So what is the cosine of our theta, okay? So when you're dealing with the unit circle, or it doesn't even have to be the unit circle, right? You've got x is the horizontal, y is the vertical, and radius. The radius is the hypotenuse, is the radius of the circle, whether it's a unit circle or whatever circle, okay? So there's your radius. So the cosine of your angle is adjacent over hypotenuse. So it's x over r, the hypotenuse is the radius, and x is the adjacent side, right? The horizontal side is x, the vertical side is y. So what does x equal? Multiplied by r, x is r cosine theta. That's where these conversions come from, way back, your trig class, right? All right. And then what about y? What about our y conversion? Well, the sine of theta is opposite over hypotenuse, y over r. So multiply both sides by r, your y is r sine theta. That's where it comes from, okay? All right, x squared plus y squared equals r squared. That's just Pythagorean theorem, okay? So that's just the Pythagorean theorem on this, okay? So, all right, that's just the Pythagorean theorem. And then tangent theta equals y over x. We hardly ever use that one, okay? When you're converting rectangular to polar, you want to change all your x's to r cosine theta, change your y's to r sine theta. dA is r drd theta. There's an extra parameter in there. It's the r. Don't forget that there's an extra r in there. Okay, don't forget, that's huge, okay? Why? Because you're going from the XY plane to the polar grid. And so instead of dealing with rectangles, we're dealing with like sectors. Okay, so sectors of a circle. So sectors, you've got that curve in there. So it's an arc length parameter, and the d theta is taking care of the angle, but you've got that extra arc length in the that extra parameter in the arc length. So you've got to incorporate it in there. You just need to remember to put that there. Okay, we good? Remember all this? Okay, so let's do example. Okay, so let's do another example. All right, this is what we were going to do if we had time to do, or maybe this is the one we were going to do if there was time last time, okay? But let's do this one, okay? So D is the region in the first quadrant bounded by the lines y equals 0 and y equals radical 3 times x, okay? And the circle x squared plus y squared equals 9. That's the base. So we have to sketch the base, right? And we want to do this in polar, right? It doesn't necessarily tell us to do it in polar, but you see all the x squared plus y squareds? So we want to do this in polar, all right? So let's go ahead and sketch the base. It's the region in the first quadrant, okay? So I'm just going to draw myself a graph to incorporate just the first quadrant, all right? So my graph is going to be first quadrant. Okay, so now what do I have in the first quadrant? The line y equals 0. Okay, well, the line y equals is a horizontal line. So the line y equals 0 is the x-axis. I'll just go over it. Okay, that's a line y equals radical 3 times x plus 0. That goes to the origin. So radical 3 times x. Okay, so radical 3 times x. Here's y equals radical 3 times x. Okay. So this is y equals radical 3 times x. All right. And this circle, okay, so this is a circle, all right? So this is a circle in the first quadrant circle, right? So we want the first quadrant circle, okay? And the radius of the circle is 3 because it's x squared plus y squared equals r squared. Okay, so the radius is 3. All right, and so we have here's our region right here. It's this side. Do you see it's this side? Because it's what's enclosed by the blue markers. Okay, so it's enclosed by, so here's the bottom. Okay, here's the top, and then here's this here. Okay, so we have to figure out, all right, so that's the base. All right, so now let's go ahead to our integrand and let's adjust the integrand. Okay, so what do we have for this integrand? All right, well, x squared plus y squared, let's go ahead and make our conversions right here. What is x squared plus y squared equal to? That's your r squared. Okay, and that's going to be raised to the 3/2 power. Is that okay? All right. You could change x to r cosine theta and y to r sine theta, but then when you simplify that 5 steps later, it's r squared. X squared plus y squared is r squared. These are the conversions you have, okay? X to r cosine theta, y to r sine theta. If you happen to have an x squared plus a y squared here, save a lot of time and just put r squared in, okay? So r squared. What do I do at dA? Okay, so dA is r dr d theta. That's what dA is. It's r dr d theta. Okay. What are the bounds? What are the inside? But the inside bounds are the radius. What about the inside bounds? What are those inside bounds? Okay. Do you see it's 0 to 3? Okay. Now, what about our theta bounds? What about those theta bounds? We talked about this last time. That's why, because we were talking about this last time when I was putting examples together for today, I went and took this one. Okay. So what do you remember about this? So remember that, so we need our theta bounds. Okay. So our theta bounds definitely goes from 0 to where? Okay. So our theta goes from 0 to where? All right. So we need to know what that angle is, don't we? Okay. And how do we figure it out? Do you remember that tangent theta? Okay. So tangent theta is, I mean, this is where maybe your y over x comes in. Okay. So tangent theta is the y over the x. Okay. All right. And because this is going through the origin, I mean, if you think about it, okay, so if you think about what's the slope of this? Okay. What's the slope of this line? Well, I mean, so tangent theta. Okay, so it's kind of like y minus 0 over x minus 0, right? If you subtract this point right here and this point right here, this is the origin. Okay, so it's like y2 minus y1 over x2 minus x1. So your tangent theta is always equal to the slope of the line. Okay, so your tangent theta, when your line passes through the origin, when a line passes through the origin, the tangent is the slope. We were talking about this last time. It's a pre-calculus, or maybe your college trig class, it's wherever. So your tangent theta here is going to be equal to that slope of that line, okay? And the slope of this line, the y equals radical 3 times x plus 0, the y-intercept is 0. Anytime you have a line passing through the origin on your, on your graph, tangent is the slope of the line, okay? So where is the tangent equal to radical 3? Where is the tangent equal to radical 3? All right, on your units. Is it pi over 6 or is it pi over 3? It's one of those two, right? Pi over 6, your ordered pair is radical 3 over 2, 1/2, okay? And then pi over 3, it's 1/2 radical 3 over 2, okay? So which one of these, when you take the sine divided by the cosine, the tangent sine divided by the cosine, which one of these is going to give you a radical 3? All right, when you take sine divided by cosine, isn't that going to be pi over 3? Okay. So isn't that what it's going to be? So there's your upper bound. It's pi over 3. Okay. So you see how we're getting the upper bound there? Okay. So the upper bound's pi over 3. Okay. So that's how you're going to get the upper bound. So this is what that angle is. That angle goes from 0 to pi over 3. Okay. You need the span of the angle. Okay. All right. So yeah, it's all right. So I know you got some different stuff over there, but pi over 3. So then integrate. Okay, so what am I integrating? Well, let's see. R squared to the 3/2 power. So when you multiply the exponent, you get r cubed times the r. So we're going to integrate from 0 to pi over 3. Okay, we're going to integrate from 0 to 3. I guess that's going to be r to the 4th, drd theta. When you combine all the r's together, when you take r squared, raise it to the 3 halves, and then multiply by r, you get r to the 4th, okay? So 0 to pi over 3, and then it's going to be r to the 5th over 5, okay, from 0 to 3, and then we'll do theta that when we're done. All right, so 0 to pi over 3. Plug in, so 3 to the 5th is what? 3, 9, 27, 81, 243. So it's 243 over 5 minus 0, okay? And we want to integrate that with respect to theta, okay? So you're going to end up with 243 over 5 theta, and that goes from 0 to pi over 3, okay? So we end up with what? So we end up with 243 over 5 times the upper bound pi over 3, subtract minus 0 from that, okay? And we can cancel here, okay? So 3 goes into 3 once, and 3 goes into 243 81 times, okay? So final answer for this, okay, so final answer for this is going to be 81 pi over 5. There's your final answer. Okay, so that's what it is. That's what it is. Okay, so there's your final answer. This is how you get the bounds. This is how you work polar. We like polar. Okay, converting to polar makes it so much easier to convert to polar. All right, than to try to integrate this using, use substitution or whatever you're going to use. Okay, and trying to make the bounds go from 0 to radical 3x. Would be the inside bounds. If you did dy dx, then you would have to integrate this. The inside bounds would go from 0 to radical 3 times x, and the outside bounds would go from like 0 to 3. I mean, it's possible to do rectangular also, but it's so much easier to transition over to polar. Okay, I'm not going to take the time to do this in polar and rectangular, but when we see x squared plus y squareds there, converting to polar is something we like to do. Okay, so we do like to do that in Calc 3. All right, just makes everything so much more manageable. Do you have any questions on this one? Are you okay with how we got the theta bounds here? See how the theta bounds, okay? The inside bounds are the radius bounds, okay? And then the outside bounds are the theta bounds. So you got to look from, you're going counterclockwise. This is going from 0 to pi over 3, the span of the angle, okay? And so yeah, that's just because it stops right here at this, okay? So I know the last time we did the y equals x was our line, and we had a little conversation as to how do you know that if it's y equals x that the angle is pi over 4. So I wanted to address this kind of an example with that concept again, so we're making sure we know how to set up the bounds. The bounds are huge, okay? All right, are we ready to move, or is the pace okay, or do I need to slow down, or are you okay? Do you want a public or private message in the chat bar? Can we move? Are you with me? Are you there? Participants, 26. All right, our pace is good. Okay. So just a little communication in the chat bar. You can do it. You can do private message if you need anything. So we want to explain the r to the 4th. Someone wants to know where the r to the 4th came from. So I simplified this here. All right. So let me grab another color. So when you take r squared, all right, so let me see if I can so when you take the r squared and you raise it to the 3 halves power, and then you multiply by that r out here, right? So I combined all these. Okay, so it's not writing. So I'm just trying to so I combined. So when you're combining all these, r squared raised to the 3 halves times r. So when you multiply the exponents, okay, this is a power raised to a power. You're going to multiply the exponents, right? So you're going to get r to the what? 6 halves power. Okay, all right. When you multiply 2 times 3 halves, you get 6 over 2, which is 3. So you get r cubed times r, and there's your r to the 4th. Okay, so that r to the 4th, when you simplify the r's there, you're at r to the 4th. Okay, do you see it? All crystal clear? All right, so that's your, let me try to, so there's the r to the 4th without writing through it. Okay, so that's simplifying to get, so there's the r to the 4th. Okay, I just took all those r's and made the substitution. We had to simplify it. Okay. All right, anything else? It was just a private thing to explain that, which is good. Just anything you need to seize to make it crystal clear, just say something. Okay. All right, let's do the next example. Let's do this one. All right. D is the region, it's a semicircle. X equals 4 minus y squared in the y-axis. So it's a semicircle. So how are you guys? So where is the semicircle? To the top half, bottom half, right half, left half? I'm dealing with a semicircle, but where is my semicircle here? Is it the top, the bottom? This right here, it's x equals, okay? So the radius is going to be 2, all right? So it's a semicircle, but where is it? Top, bottom? So if you take x squared plus y squared equals 4, okay? That's a circle radius of 2, right? Okay, so this is a circle. Radius equals 2. That's what we have right there, right? Okay. All right. So that's a circle, radius is 2. Okay. So now let's go ahead. And so if you subtract x squared from both sides and take the square root, so y equals radical 4 minus x squared. Okay. So if you have y equals radical 4 minus x squared, okay, if you have this, that is going to be the top half. There's the top half. Okay. All right. What if we have y equals negative radical 4 minus x squared? Okay. So what if we have negative radical 4 minus x squared? You know what that is? That is the bottom half. All right. You good so far? Okay. So now what if we are dealing with, instead of y equals, okay, what if we subtract y squared from both sides, okay? So subtract y squared, so x squared is 4 minus y squared, take the square root. What if we have x equals radical 4 minus y squared? What if we have this, okay? Well, this is going to be the right half, okay? This is the right half of my circle. Okay, this is the right half, okay? And then might as well finish it off, right? What if we have x equals the negative of radical 4 minus y squared? What is this going to look like? This is going to be the left half, okay? So this is going to be the left half, all right? All right, so are my scribbles down there making sense to you, okay? All right, so these are the pieces, so, so this is a circle. Okay, so, and it's not a function, right? Because it's a circle, so not a function. So y equals, so when you get it to y equals, okay, y equals the radical expression top half, y equals negative the radical bottom half, right? So there's your top and the bottom when it's y equals. When you got x equals, you can deal with the right and the left, okay? X is the positive radical expression to right, x equals the negative to left, okay? So I need to graph my base up here, okay? So do you kind of see that this is just all, this is just kind of, so this is just a sidebar, right? This is like a sidebar, right? This is just, when do you learn this? This is pre-calculus? When you're doing conic sections and stuff, okay? So pre-calc review, all right? I hope the review stuff, all the fun stuff that from the past I hope that's not too much from the past, okay? All right, I just want it all to be like super crystal clear. So, so now we want to graph this. So x equals radical 4 minus y squared. Okay, so I broke that all down. Can we all see that's the right half of the circle? So let me graph that. And that's going to be the right half, isn't it? Okay, so that's the right half of the circle, and its radius is going to be 2. So the radius is 2. So you got the right half of the circle, okay, and then so the right half of the circle and the y-axis. Okay, so there is our closed-in boundary region right there. Okay, so there's what we're dealing with. We're dealing with this right here. There it is. Okay, do you see it? All right. So now let's go ahead and set up our, and we're totally going to change to, this is going to be e to the negative r squared. We're totally using polar. We're converting, okay? So you factor out the negative and you have an x squared plus y squared. So e is a negative r squared. All right, dA, what do we do with dA? It's r dr d theta. You don't even have to think about that. You just make that substitution. You don't even have to think about it, okay? Inside bounds are the radius bounds, okay? Inside bounds, the radius, right? Look, it's prescribed to us because we don't even have to worry about it. This is how we do polar. I'm telling you, in Calc 3, we like polar, okay? Calc 2, it's just, I don't know what kind of images of polar in your mind from Calc 2. Some of my students like doing polar problems, some of them don't. But Calc 3, we like polar, okay? It's a lot easier to integrate than this stuff in rectangular. Okay, so r d theta. So the inside bounds of the radius, can you see we're going from, you go center out. So the inside bounds, does everyone see 0 to 2? Okay, so 0 to 2 for the inside bounds, okay? Now the outside bounds, here's where you got to be careful, okay? You got to be careful with this one, right? So the outside bounds, well, you're going from here to here. Now where is from here? Going to have to call that like negative pi over 2 to pi over 2, okay? You kind of have options for the outside bounds, okay? So is it okay to do half the theta bounds and double it? Yes, good point. Yeah, because of symmetry, right? So you can go from 0 to pi over 2 and double the whole thing, okay? And because we have to do so much of this by hand, that might even be easier to do it that way. Good point. Thank you. Okay, I wasn't even thinking of bringing that up. Because of symmetry, the question, oh, you see the question because it's public, so thank you, Sean. So can you go from 0 to pi over 2 and double it? Yeah, because you have a symmetric base, so you can totally do that. All right. Now, some people are like, well, isn't that 3 pi over 2 there? Well, if you call it 3 pi over 2, you'd have to go from 3 pi over 2 to 5 pi over 2. You could call the bounds 3 pi over 2 to 5 pi over 2. Okay. All right, so 6 pi, you can go 7 pi over 2 to 9 pi over 2, and that would work, right? You have all these infinitely many ways to say those bounds, right? You do, by the way, for the outside bounds. So, but negative pi over 2 to pi over 2. All right, questions on the setup. Okay, so questions on the setup. You're good with the setup. So let's go ahead and evaluate this. Okay, I hope I have enough space because I did our little pre-calc unit there. So let's go ahead and evaluate this. So how would we evaluate this? Use substitution, exponential function. So let u equal the exponent. Okay, it's not writing. So let me go back and unfreeze it. U is the exponent. So du, okay, is going to be negative 2r dr. So du over negative 2r is going to be the dr substitution. So the r's are going to cancel, aren't they? Okay, so rewrite the integral. So we have the negative pi over 2 to pi over 2, which I may do the doubling thing in the next step. Okay, and then we have, we're integrating e to the u. Okay, and then you have the r, and then dr is du over negative 2r. Okay, and then the d theta out here, but we're going to concentrate on this right now. All right, the r's cancel. Okay, so we're going to make the r's go away, and you're in. So pull out your negative 1/2. Okay, so you have the negative pi over 2 to pi over 2 is hanging out here. We're not ready for that yet. Okay, so bring out the negative 1/2 and integrate e to the u. You get e to the u, which is negative r squared. E to the u integrates into itself. Okay, we want to evaluate this from 0 to 2. And then we'll integrate with the thetas next, okay? So, all right, negative pi over 2 to pi over 2. Okay, that's hanging out there. All right, negative 1/2 here. Integrate, plug in the upper bound, so you have e to the negative 4. Plug in the lower bound, you have e to the 0. Anything to the 0 power is 1, okay? And then integrate that with respect to theta. That's a number, okay? So that's just a number. So, all right, and this is where, can I just go ahead and do the doubling thing? So we can just plug in 0 for the upper bound, pi over 2 for the upper bound and 0 for the lower, okay? So I'm going to double it, okay? All right, so since symmetry, all right, we can double and go from 0 to pi over 2, okay? So the negative 1/2 e to the negative 4 minus 1. Okay. So just go ahead and integrate. That's a number. So you have the two. So the twos are going to cancel. All right. So we can go ahead and these twos are going to cancel. Okay. And then we can go ahead and call it negative. Well, I can just flip that around, right? Distribute the negative. So it's 1 minus e to the negative 4. Okay. So it's 1 minus e to the negative 4. All right. And then that's multiplied by theta. Okay. And then evaluate this from 0 to pi over 2. All right. And so when you do evaluate it, you're going to have your final answer is going to be pi over 2 times the quantity 1 minus e to the negative 4 power. Okay. And that's it. So you'll get through the actual integration part, but you know what? Setting it up, okay? Set it up. That is huge. Making sure that you get the bounds correct. Make sure that you do the conversions correct. So conversion to polar. We like conversion to polar, all right? So yeah, and it fit on this page. Okay, so let me know if I need to write anything neater, but yeah, we talked about which semicircle piece is where. All right. So we have the right section with the bounds. All right. Okay. So questions with this? You're okay to pace okay? So just, you could just privately just say, slow down if you want me to slow down or, all right. So next page, I don't even know what's on the next page. I think we're going on to the next section right now. Do I have one more example on the next page? No, we're going to go on to 15.4. Okay. So what time is it? 5:15. So we just spent the first 45 minutes going over homework 3 and then reviewing. Okay. So we reviewed polar and we reviewed rectangular and polar. Okay. So we're done reviewing this. All right. I doubled it, but when I doubled it here, so instead of going negative pi over 2 to pi over 2, I doubled and went from 0 to pi over 2, but then when I doubled it, do you see the 2's cancel? That 2 and the half cancel, okay? So the 2 and the 1/2 cancel, so with the double in it, okay? All right, Brittany, I see that you're here, something like that, thank you. So good, you see all the pieces? All right. And just kind of keep practicing these. So this was number 11 in your book, but you still have to go back and do number 7, 9, 11, 13. Do practice the syllabus problems. Okay. I mean, I only had 2 of them on that worksheet. It's not enough you just got to practice. You just got to just practice them. Okay. So let's go on to 15.4. So center of mass. My page isn't turning, so sorry again. I got to do this. I need to make a background photo on my iPad screen of, I don't know, something calculus 3 for you, so you don't have to see me and my daughters all the time. But all right, so application of double integral. So we need to go over, what do we use double integrals for? Well, center of mass is a huge thing. Okay, center of mass, we don't have time to do every single thing. Okay, we don't in here. I'd love to, but we don't have time to do every single thing with inertia and just so much. But you know what? You're going to do it in your physics class. So those of you that are taking calculus-based physics, you're going to bring your double integrals there. So you're going to get all this in your physics class. All right. But let's at least do a center of mass, because I know in Calc 2 you have to cover center of mass, or hopefully you did cover center of mass. Okay. And if you did, great. And if you didn't, we'll pick it up here. Okay. So how can we use double integrals in an application? Okay, in an applied context, okay, in an application. So where would we use double integrals in real life? Here's one place where we would use them. So applied mathematicians are interested in center of mass, okay, because if they know where the center of mass is, you can control a system, okay. So some of this stuff is just like my words, right? Okay, so in my 2 cents worth, it may not be written like this in your book. You can read your book to get the I don't know, just to get the technical stuff, all right? But these are my words. You can think of center of mass as a point where the mass is concentrated at, okay? I mean, I didn't even know that that's a complete sentence, all right? And I ended the sentence with the word at, which is probably a no-no in the whatever. Okay, example. So where would you use center of mass in real life? Okay, so in designing a Formula One car, all right, engineers like to know where the center of mass is. Okay, you figure out where the center of mass is. And they like to keep, for Formula One cars, they like to keep the center of mass like as low as possible to the ground because the cars handle better, they go faster, right? Okay. So, I mean, there's reasons. You know those cars. Those cars are always so low to the ground, and so this is so mathematically, this is how you would figure out where the center of mass is. Okay, so to get the center of mass, these problems are huge, long, really, really long problems. Okay, so I'm going to post homework 3 probably this week. It's not due for a couple of weeks. Okay, one of your problems on homework 3 is a center of mass problem. It's going to probably take 2 pages to do the one problem. So when you see me post homework 3 and you look at it and say, oh, wow, check this out. Homework 4, I'm sorry, you already turned in homework 3. I'm probably going to post homework 4 this week, okay? So homework 4, yeah, it's due the 23rd, which is like, is it 3 weeks from today, right? It's 3 weeks away, but I'll post it this week. And when you see it, you're going to be like, wow, there's only like 7 problems on here, or 8 problems total, okay? That's because they're kind of long, all right? Wait till you see what we're doing with this one, okay? So they're kind of long. So, and you can start at any time, so you're going to have, on homework 4, you're going to have a center of mass problem like this, okay? And you're going to have some surface area problems on it, like what we're doing today, okay? And you're going to have triple integrals on there, and if all goes well, we get into all that today. You can start homework 4 now, and it's not due for 3 weeks, all right? All right, because they're the applied problems, all right? Like homework 3 was just computation. It's just computation, okay? But homework 4 is applied, all right? So the problems are longer, okay? Making a review before. Yes. So you got another test to go, and I'll make a review, and then you'll have a final exam. Yeah, I'll probably stay in that mode. Yeah, I'll probably do that. It helps. So yeah. Okay. So yeah, so you'll see. Let's see what you think. Okay, so long problem is a difficult problem. No, they're not. I don't think this is difficult. You be the judge. We're going to do this one, and we're going to see what you think when we're done. Okay, we want to find the center of mass. Our examples on the next page. Okay, so we have formulas you need. These are the formulas. Okay, so you need the mass formula. Okay, so the mass formula is this here outside of the XY. This is Greek letter rho. Okay, this is Greek letter rho. All right, so when you're using this in a math class, science class, Greek letter rho is density. It stands for it's how we represent density. Okay, and it's a variable density, right? You got a variable density, so that's why we did double integrals, because you got the density and then you got the distance thing, and they're both variable. Okay, that's why we have a double integral. So this is the density. All right, so the mass is adjusting for the variable density, okay? So to get the mass, you're going to set up a double integral, okay? You're going to set up a double integral, and we're only doing one example of this because you'll see why, because it's long, okay? Then you get your moments, okay? So your moment about the x-axis, moment about the y. It's first moment about the x, first moment about the y. Okay, that's what they call them. Okay, so your moments are, you're going to have your density, but you're going to incorporate the y times the density. The y because you want the density, but you want it relative to how far you are away from the x-axis. Okay, so that's why you're multiplying it by y, because your moment about the x, so you're at the x-axis. So you want to take the density and then how far you are away from the x-axis. So that's why you're using the y out in front. Okay, and then your moment about the y is going to be your density, but then you're going to multiply that by the distance you are away from the y-axis, which is going to be the x representation. These are your formulas. Okay, so these are your formulas. So get them down. They're in your book. Okay, they're in your book. Get them down, written down somewhere. So once you get your formulas here, the center of mass, it's the exact same. This center of mass that I circled in red is the exact same formula as it was in your Calc 2 class with center of mass, okay? In Calc 2, you should have done center of mass problems, but you kept the density constant and you just kept the one variable. So you set up like a single integral instead of a double, Okay, that's what you did in Calc 2. So in Calc 3, we're going to have variable density. So that's why we have a double integral. But you're still going to, for your center of mass, you're still going to take the moment with respect to the y divided by the mass, and the moment with respect to x divided by the mass. All right. So if you looked up in Calc 2, this is the same exact way you get the center of mass, except for we have to evaluate a double integral. Okay. Examples on the next page. All right, the examples on the next page. So I don't know if you're going to screenshot this or if you're writing it down. Okay, hopefully I kind of talked enough through it that you got down whatever you want written down. You really need the formulas down here is what you need. Okay, you don't need my 2 cents worth up there. You don't have to look at my words if you don't want to look at my words. Okay, so we want to just do a mathematical application problem of what we would possibly, if you're going to be the engineer, the analyst, to figure out, if you're doing with the Formula One cars or wherever you want it, whatever you're applying this to, okay, finding the center of it. And you could probably Google and find 1,000 different more things that you would use this for, okay? But I thought we would concentrate on the center of mass for our example, just because we did this kind of thing in Calc 2, all right? And if you didn't do it in Calc 2, this is the process that you would have used. This will cover Calc 2 and Calc 3 if you didn't go through it, okay? All right, turn the page. You ready for the example? All right, so here's the example we're going to do. So let me turn the page, okay? It didn't turn, so let me just go back and turn the page. Here's the example. So we want to find the center of mass of the lamina, that's what they call it in the book, that occupies the region D. It has the given density, and it has the given function. So does the line above the X and Y? Oh, it's just the symbol that they use to represent the center of mass. It's a symbol that they use. It's almost like, so if you see X bar, Y bar, it's just centrally located. So that's your center of mass. Yeah, I mean, if you see X bar in a statistics class, it means sample mean, right? It's something different. So it means a sample mean. It's the average of the system. So we're looking for the center of, so just kind of the center. So maybe that's why they use it, because it's like so they use that symbol. So it's X bar, Y bars, this in parentheses is what they're using for the X coordinate, the Y coordinate of the center of mass. We're going to draw pictures so you can see it on the picture and stuff. We're going to sketch it and we'll find it. All right, so it's the symbol that they use for representing center of mass, okay? So the center of the X is the center of the Y's, but we have variable density. So, if this side is heavier than this side, then the center of mass might be way over at the edge instead of in the middle, all right? So X bar, Y bar, a lot of different, so in a stats class, it means sample mean, but we're not in a stats class, we're in a Calc 3 class, so this is just going to be the center of central location. It's the notation they use, all right? All right, so that was just a private question. What's the line above it mean? It's just a symbol, the line that they use to represent it. Okay, so we're going to go back to, so let's take a look at our example. And it just keeps freezing when I sit on one page for too long. Find the center of mass of the lamina. Okay, so what do we need to do first? We need to get the base here. Okay, so we need to figure out what the base is so we can start evaluating our double integrals. All right. So let's sketch a picture of our base. All right, we'll use a different color. So we use purple. All right, so y-axis and x-axis. All right, so we have x equals 0 is the y-axis. So there's one side. Okay, so x equals 0 is the y-axis. It's one side. Y equals x is one side. And 2x plus y equals 6. So y equals negative 2x plus 6, right? Okay, so 2x plus y equals 6. So y equals a negative 2x plus 6. Y-intercept is 6. Slope is a negative 2, so it crosses the y-axis at 6. The slope is negative 2, so here's our region right in here. Okay, so this is our region right in here. All right, so that's what it is. Okay, so use a skinnier line. So there's our base. All right. Y equals x is here. Okay. Y equals x. I want to use a different color. So I'm going to put y equals x is this line. okay? Y equals 6 minus 2x is this line, okay? So I want to, so let me, so what do I have to do here? I have to find, I'm going to have to set up a double integral. Let's find the mass first. Hmm? Someone question, we're good?
Bro, you guys need to trust people, bro.
Hello, your audio is on. I don't think that was, all right. So, you guys okay? All right. So so we have to find all these pieces, right? We have to find the mass. We have to find m sub x, m sub y. We got to find the mass and the moments. Okay. So let's start with the mass. All right. So let's find the mass first. Okay. So let me use this color. So the mass is going to be a double integral. Okay. It's rho x, y, dA. Okay, and then that's our D down here. So we got to set it up. Okay, so let's do that first. Okay, so I'll just try to do this with the formulas there. So we're going to find the mass. So it's a double integral. All right, now what is our rho function? It's x squared. Okay, so x squared. Okay, now look at our base. Do you want to do dy dx or do you want to do dx dy? You want to go this way and do dy dx. Okay. All right, so is that okay? So let's do dy. So what are our inside bounds? Okay, so we do dy dx. What are the inside bounds? It goes from here to here, bottom to top. Inside bounds, can you see what it's going to be? It's going to go from x to where? 6 minus 2x. Okay, there's the inside bounds. Yep, good, thank you. Okay, all right. The outside bounds, okay, it's going from 0 to where? It's going from 0 to here. I need the point of intersection. Okay, so I need to get the point of intersection so I know my upper bound. I need the point of intersection. Okay, so the point of intersection between what two lines? Well, look at where they intersect, between 6 minus 2x, 6 minus 2x, and x. So to get that point of intersection, I got to set the curves equal to each other. I set this line equal to that line, okay? Add 2x to both sides, so 6 equals 3x, okay? Divide both sides by 6, so x is 2, okay? So the x coordinate of the point of intersection is going to be 2, all right? So x equals 2. All right, so this point right here is going to be 2, 2, I guess. That's what that point is, okay? So that point is going to be 2, 2. All right, so let me just see here. All right, so 0 to 2 would be the outside bounds, okay? So you see how you set it up? You're setting up a double integral, all right? And then we are going to solve it, all right? So let's go ahead and, this is for the mass, right? So what is the mass going to be? Well, we'll take care of the 0 to 2 in a moment, but let's go ahead. We're integrating x squared with respect to y. So we integrate with respect to y, you get x squared times y. X is treated as a constant. This gets evaluated from x to 6 minus 2x, okay? And then so we have to evaluate it. All right, so to get the mass, okay, all right, we'll integrate from 0 to 2 when we're done with this, but plug in the upper bound for y. All right, plug in the upper bound for y. So distribute, you get 6x squared minus, plug in the upper bound, 2x cubed, okay? Plug in the lower bound for y, you get x cubed, okay? You get x cubed when you plug in the lower bound, okay? And then we're going to integrate with respect to x now, okay? So plug in the upper bound. When you plug in the upper bound for y, I'm distributed, right? So I distributed, so 6x squared minus 2x cubed. When you plug the lower bound in for y, you get this, okay? And we can simplify that. We can actually combine the, let me go one more step. We can combine those, okay? So let's go ahead and combine them, okay? So the mass, and we'll integrate from 0 to 2, okay? So you're going to have 6x squared, all right, minus 2x cubed and minus another x cubed, so minus 3x cubed, okay? All right, and we want to evaluate, okay, so we want to integrate this. So the mass is going to be 6x cubed over 3, okay? So 6x cubed is 2x cubed minus 3x to the 4th over 4. We want to evaluate this from 0 to 2. So the mass is, plug in the upper bound. So 2 cubed is 8, so you get 16 minus 2 to the 4th, 2, 4, 8, 16, 48 divided by 4, 12. Plug in the lower bound, you get 0 minus 0. So the mass is 4. Okay, so the mass is 4. Want to double check that? Okay, so the mass is 4. We need that. Okay, so we need that. All right. So how are we doing so far? So what fraction of this problem is done? What fraction of our problem is done? Let's see. We want to find the center of mass for this region right here. There's our base. Okay, so what do we got here? Well, we have to find the mass. We found the mass. Okay, we got that. Now what do we need? Got to get the moment for the x. We've got to get the moment for the y. And then we got to put it all together. So you're saying about 1/4 of the problem's done. Yeah, we're about 1/4 of the way. We got the mass. Okay, now let's get our moments. Okay, so we're going to get the moment with respect to x. So you're going to take it's going to be y times the function they gave us to represent the density. Okay, all right, so it's going to be that. So we're here, all right, and I need I need a few more pages for this problem. So let's go to the next page. All right, I'm going to keep this page. So here's what I'm going to do. I'm going to go ahead and copy the page, okay, and then I'm going to paste it on the next page, okay, and I'm going to get rid of this, okay. So I'm going to move this out of the way because it's on the previous page, okay. So it's on the previous page. This is on the previous page, okay. So that's on the previous page. All right, you good? See, it's on the previous page. All right. So let's take this page now. Okay, let's take this page and let's go ahead and find our moment. Okay, do you remember what the formula was for that? Your double integral setup? It's going to be y times your density. Okay, so the moment with respect to x, that's the y, because it's the distance from the x-axis, right? And the distance away from the x-axis, you got to put the distance in there with the density. Okay, now you got to take both into effect. Okay, so let's find our moment with respect to x. Okay, so how do we do that? We do exactly what this tells us to do. Okay, what is the integrand going to be? It's going to be y times our density function, which is x squared. Okay, now because we already set up the mass, okay, and you saw what we did here, so just make sure you did that right because you're just going to follow suit. So let's just do dy dx like we had the other one set up, okay, and it's the same base for all of them. So whatever you did for the mass, you're going to do for the moments, both moments, okay. So the inside bounds go from x to 6 minus 2x, okay, and then the outside bounds are going to go from 0 to 2. All right, so the outside bounds go from 0 to 2. Your inside bounds, because we're doing dy dx, your inside bounds x to 6 minus 2x, outside bounds go from 0 to 2. Okay, and then you evaluate this. Okay, so you get the moment with respect to x. Are we good with the formula over there? Okay, so the moment with respect to x, so you have 0 to 2. Okay, integrate with respect to y. Integrate this with respect to y. This is going to give us y squared over 2 times x squared, isn't it? Okay, we want to evaluate this from x to 6 minus 2x, okay, and then we'll do dx here, okay, so y squared, so moment with respect to x, okay, moment with respect to x is going to be what? Plug in for y, so I've got the 0 to 2, I'll pull out the 1/2, and I have 6 minus 2x quantities squared times x squared. There's your upper bound, okay? All right, minus, and then your 1/2, okay? Plug in your lower bound, so it's going to be x to the 4th. All right, so there's your dx. All right, so make sure we did that okay. So plug in the upper bound, and you're going to have 6 minus 2x quantities squared times the x squared over 2. Plug in the lower bound, x to the 4th, x squared times x squared. We need to integrate this. So am I going to just multiply it out? I've got to be careful here. Okay, what's the easiest way to integrate this? Let me just FOIL it out. Okay, so let me multiply this out. So I've got the 1/2 up front. So I have 36 minus 6 times 2, so minus 24x plus 4x squared times x squared minus x to the 4th over 4. All right. Distribute the x to the 2nd power. So distribute the x squared. So the moment with respect to x, I'm going to distribute the x squared over 2. So half of 36 is 8. So 18x squared. All right. Half of 24 is 12. So 12x to the 3rd. Okay. Half of 4 is 2. So 2x to the 4th. Minus x to the 4th over 4. Okay, so let's just integrate this and evaluate it. Okay, so the moment with respect to x is going to be 18x cubed over 3. 18x cubed over 3, so what's 18 over 3? So 6x cubed. Okay, 12x to the 4th over 4. 12x, so 12 goes into 4, so 3x to the 4th. Okay, 2x to the 5th over 5. Minus x to the 5th over 5 times 4 is 20. 0 to 2. Moment with respect to x, plug in the upper bound, so 248 times 6 is 48. 2 to the 4th, so is 16 times 3 is 48. 2 to the 5th, so 2, 4, 8, 16, 32, 64 fifths. Minus 2 to the 5th is 64 over 20. And then plug in the lower bound, you get 0. 48s cancel out. So what do we end up with when we evaluate this? So you get 64 over 5 minus, this reduces, right? 4 goes into 64 16 times. 4 goes into 20. 4 goes into 25 times. So it's 64 minus 16. Two, 4, 8, 16, 32. Oh, hang on. Are you guys following along with me? I think I made a mistake there. Distribute, because what's 2 to the 5th? I put 64 again because of that one over there, but 2 to the 5th is actually 32, isn't it? Okay, I made a mistake on that. All right, so let me just put it in a different color. So this is minus 32 over 20. Okay, all right, and then plug in the lower bound, and you get 0. So, so you have 64 over 5 minus 4 goes into 32. 4 goes into 20.
Professor, couldn't you have done 2x to the 4th minus x to the 4th divided by 4? Wouldn't that simplify that a little bit?
It would, but hang on to it would. So 64 minus, all right, 3x to the, so 2x to the 5th over 5, and that's going to be x to the 5th over 20, and that's that, and that's that. So 4 goes into 32 8 times, 4 goes into 25 times. 64. All right, what's wrong with this? You see anything here? Yes, no?
Professor, how did the x to the fourth 1/2 turn into x to the fourth over 4.
Bingo. Thank you. Bingo. I must have accidentally, right up here, I must have accidentally multiplied that. All right. I must have accidentally, when I was doing the 1/2, I must have accidentally multiplied that. Okay. So where's my mistake start? Here. That should be a 2. That should be over 2. Okay. So, all right. I made computation errors, guys. All right. I'm going to fix it right now. Okay. So this should be x to the 4th over 2. This should be x to the 4th over 2.
I think it's frozen, Professor.
Okay. It needs to be frozen because I'm making a mess. Okay. So I'll use the different colors. Sorry. All right. So this is minus x to the 4th over 2. This is minus x to the 4th over 2. This is minus, I'm integrating x to the 5th over 10. Okay. So I accidentally put this x to the 4th over 4 when I brought this down. I just brought it down, but I put it over 10. So we're here. So when you integrate, when you evaluate this, it's 32 over 10. So half of 32, so 16 over 5. So 48 over 5. All right. There's that piece that we need. Okay, 48 over 5. Okay, that's what it is. That's the moment with respect to x. So are we almost done? No, we've still got the other half of the problem to do, right? So let's do the other half. Okay, so moment with respect to x. So it's going to be y, distance from the x-axis, right? Distance from the x-axis times the density. And then you have to set it up. Density is x squared times y. And so you have to set up your base. They give you the base. So you set up the base. All right. So, all right. Right. And this is our base. The center of mass has to come out inside this triangle, right? Our answer needs to be inside this triangle. If we do all this work and then we get a point that's like up over here outside the triangle, then we got to go back and fix it. But it's good so far. All right. I'm trying to be careful. This is a long one. All right. Can I turn the page and do the next part? So we got to get the moment with respect to y next. Okay. So I'm going to paste that page, but we're going to make all this go away, right? Gonna make this, we already did this. Okay, so this is pasted from the other one. Okay, so I'm just, so I can have these pieces here. Let's find our next piece now. So our next piece is, we want the moment with respect to y, is what they call it. So it's your double integral, but it's going to be the distance from the y-axis. So, all right. So it's going to be the distance from the y-axis times our density, dA. Okay. So see what we're doing? So these are our formulas. These are the formulas, and we're doing center of mass problem. We're doing one center of mass problem. So we have to get these pieces right. We got to get 1, 2, 3, our 3 pieces to put it together and make our 4th part. Okay. So there's your first piece. The mass is 4. Hang on to that. The moment with respect to x-axis is 48/5. Okay. Those are the pieces over there that I messed up on in case you, okay, so I did it in a different color so you can see the fix. Okay, and it's fixed now. All right, let's do the moment with respect to y real carefully, okay? So moment with respect to y. So you set up your double integral. It's going to be x times x squared, okay? So x, distance from the y-axis, times the density, dy dx, okay? All right, and you've already seen this on previous pages. So let's go from x to 6 minus 2x, okay? And then let's go from 0 to 2. Okay, so you've already seen how those were set up. All right. So integrate with respect to y first. Okay, so we'll take care of the 0 to 2 in a moment. So you're going to have y times x cubed. And evaluate this from x to 6 minus 2x. Okay. All right, and then we're going to evaluate. So plug in the upper bound for y, because we integrated with respect to y, then plug in the lower bound for y. Okay, so plug in the upper bound for y. So plug in the upper bound for y, and you're going to have, we have the integral from 0 to 2 out here still. So plug in the upper bound, I'm going to distribute the x cubed, so we're going to have 6x cubed minus 2x to the 4th. Plug in the lower bound with respect to y, so you're going to have x times x cubed is x to the 4th. Okay, so moment with respect to y, let me combine these. You have 6x to the 3rd minus 3 minus 3x to the 4th. Okay, well, this one doesn't look like it's as bad as the other one. This one's not too bad. Integrate with respect to x, 6x to the 4th over 4. Okay, so that's going to be 3x to the 4th over 2. Okay, 6x to the 4th over 4. 6 over 4 is 3 halves. Integrate 3x to the 4th, you get 3x to the 5th over 5 from 0 to 2. So the moment with respect to y, 2, 4, 8, 16, 48 divided by 2 is 24. 2 to the 5th is 32. 32 times 3 is 96 fifths. Plug in 0. So what's this going to be? 24 times 5, that's 120 over 5. 120 over 5 minus 96 over 5. So our moment with respect to y is what? 24 over 5? Okay. Just going to sit back and look at this for a second. 24 over 5. So make sure all the computation's correct. Okay, so that's a number to hang on to. It's 24 over 5, right? So 24 over 5. Yeah. Okay. We're still working on this problem. Okay, so we got the distance, we got the density, we got the pieces. We're just about ready to put it together. Okay. Who's ready to put it together? So ready to put it together. Okay. So here's what we're doing. We're doing a center of mass problem, an example from 15.4. We're just doing the one because it takes forever. Center of mass problem. So here's an example. So we had to find the mass. We did it on the next page. We had to find the moments with respect to x, with respect to y. Okay. So we found the mass. It's 4. Found the moment. First moment of the x-axis is 48 fifths. All right. First moment with respect to y is 24 fifths. Okay, so 24 fifths, okay? All right, and then so let's put it all together. So next page, I'm just pasting this page. So paste the page, okay? So I'm pasting the page, but hang on a second, okay? Because this is the page that I've been pasting. So I'm just gonna make all this go away. Right, we have that on the previous page, right? So I'm just kind of working all this out because it's this problem's taken us 4 pages to do. Okay. Okay, so let's put it all together. All right. So what do we have so far? We have the mass is 4. Our moment with respect to y-axis was, what was that? With respect to the x-axis. Let's do the x. Okay. So moment with respect to x, we did that first. Okay, so what was the moment with respect to x? It's 48/5. Okay, that was 48 over 5. Okay, moment with respect to the y-axis was 24 over 5. Yeah, okay. So let's go ahead and find our center of mass. Okay, so find the center of mass. So how do we do that? So x bar, the center of mass, is going to be the moment with respect to the y-axis divided by the mass. Okay, and our y bar is going to be the distance from the x divided by the mass. Okay, so x bar. So what is this going to be? Well, let's see. This is going to be 24/5 over 4. Okay, so that's 24 over 20, which is 6/5. Okay, and then then we want the moment with respect to x. So this one's going to be 48/5 over 4. So it's 48 over 20. 48 over 20 reduces to what? 12 over 5. All right. So the center of mass there's your answer. Let me double check. 6/5, 12/5. It's actually the correct answer. Okay, so this is what we're supposed to land on. This is the correct answer. All right. Let's make sure it's inside the region. Okay, so look up here at the diagram. Okay, this is at 2, 2, right? So 6/5 is 1 1/5. So you're going to go over 1 1/5, a little bit more than 1, and then 12/5. That's what 2. So 5 goes into 12 twice, 2 2/5. So you're going to go up 2 2/5. So based on our information, where is the center of mass? Based on our information, the center of mass appears to be right about here. Okay. All right, make sure it's inside the region. It's got to be inside the shaded region. If you do all this work and you get a center of mass, it's like over there, then you did something wrong. You got to go back and check it. This is it. We did it. There's the rest of it. Okay, there's your answer. So here's the center of mass problem. Okay, so center of mass, you got to find the mass, moments, put it together. So we found the mass on this page. It's 4. We found the first moment with respect to x is 48/5. We found the second moment with respect to y is 24/5. And we put it all together. Got our answer. 30 minutes. Oh, I know. Can you imagine? So, can you imagine if I put this on a test? Okay, I'll tell you right now, I will never put a question like this on a test. That's why I have to put it on homework 4. Okay, so you're gonna have to do one on homework 4, and we're not going to put it on a test. All right, so you can do the other applications in physics. Do you do this in physics also? Do you center of mass, inertia, in physics 1? Okay, yeah. So this is
physics 2, but it was more of a summation problem. Add a bunch of things up.
Physics 1, physics 2. Okay. All right. Yeah. So this is application of double integrals. Okay. This is the only application we're going to do because you can see how long it takes. Yeah. We're going to move on to surface area next. Get the applications out of the way today. I was hoping to have time to hit some triple integrals, but we'll do that Wednesday. We can wait till Wednesday. But let's do surface area. Just a formula. Surface area is easy. All the application stuff are formulas, right? Just formulas. All right. So, you do it. Electricity and magnetism is when you do center of mass stuff. Okay. Yeah. So we have to. I know. I'm just not putting it on a test. This is All right. So yeah, that's a lot to it, but you're going to have to do one of these on homework. So when you look at homework 4, did you write this down? You have a nice little good model to do. Be careful with your formulas. Okay. Check everything thoroughly. Yeah. So when you look at homework 4, what you're going to have, I'm going to put it out this week and you're going to have over 2 weeks to do it. And you see there's only 8 problems. We have 2 weeks. Well, get on it. Okay. Because some of the problems are kind of long like this. This topic is just long. That's what it lends itself to. Okay. So I teach this in Calc 2 also in my Calc BC class. So we do center of mass, but you use constant density your density is not a variable expression. Other because you don't know multiple integrals in Calc 2. Okay. And then so in Calc 3, you let your density be a variable. Okay, moving on. So we're moving on. So here we are. Surface area. Surface area. 3 dimensions. So you're going to have a plane, all right, and you got a plane region, and you're getting the area of a surface, okay? So surface area. All right, we're going to do some surface area examples. All right. So find my notes on this. Do I have notes and examples? Yeah, surface area. Okay. It's a formula. I have my clock right here. So it's just a formula. So surface area it's an extension of the distance formula. So you're going to just kind of use the distance formula and expand it to just so you have the distance and you have your boundary, and you're going to find the area of the surface in 3 dimensions, okay? So that extra dimension means we need the extra integration problem, okay? Partial derivatives involved. So you're going to have to find the partial with respect to x, partial with respect to y, square them. So 1 plus partial squared under the radical, okay? And you try to do these by hand. All right, most of these are doable by hand. So let's do this one. All right. So the first thing that I like to do before I even set up my integral, okay, this is this surface area. Now we have a bunch of examples. We're number 2 from the book, number 10 from the book, number 14 from the book. We're just going to do surface area until we're tired of doing these tonight. All right. We'll get to triple integrals on Wednesday. I like to get the z equals first, okay? So I like to get z equals, okay? And a lot of the problems in the book don't come with z equals, all right? So I like to do the 10, okay, minus 2x minus 5y. So I like to write it as the z equals first, because I need the partial of z with respect to x. I need the partial of z with respect to y. If they give you z equals, great, but most of these problems are not giving you z equal. They're giving you the equation of the plane this way, okay? So I like to do that first, okay? And then just go ahead and plug it in. So our surface area. So we're going to set up a double integral, all right? So we're going to set up a double integral, okay? And we'll do the bounds in a moment. Under the radical, you have 1 plus the partial of z with respect to x. Do you see that's -2? And you square that, and the partial of z with respect to y. Do you see that's -5? You're going to square that. Okay, so far, there's the integrand. Okay, now look, bounds and d8. Look at this. Look at our base. What is our base? It's a cylinder. X squared plus y squared equals 9. So what do you think we want to do with this? It doesn't say anything. All it says in the directions is find the area of the cylinder. Yes, we want to do polar. We definitely want to do polar, right? Okay. So your integrand is just all numerics. We don't worry about that. So we're going to do polar conversions. Okay. So what's dA? dA is, convert to polar. It's RD theta. Okay. That's what dA is. Your inside bounds are your radius bounds. And look, you have a cylinder. What is the radius? Radius is 3. Okay. And your outside bounds, it lies within the cylinder. They're not giving us any restrictions. Okay. So no restrictions means just 0 to 2 pi. Okay. So see how you're going to run and read through these when you're doing, so some of the problems in this section are going to be polar conversions, right? They're not going to tell you, hey, find the surface area, be sure to convert to polar. They're not going to tell you that. You're just going to see these areas, or you're going to see these circle formulas, right? When you see x squared plus y squared equals r squared, when you see circle formulas, do polar. We want to do polar. It makes it so much easier. All right. And then just compute this. Okay. What is that radical? 25 plus 4 plus 1. That's radical 30, isn't it? All right. So RD theta. All right. And then what do we want to do here? So then we want to, I'm going to go to a smaller size pen so I can get this on the page. Let's integrate with respect to R. Okay. So 0 to 2 pi. Okay. This is going to be R squared over 2. So radical 30, R squared over 2. Okay. Evaluate this from 0 to 3, and then we'll take care of theta. Okay. So our surface area, we'll do the 0 to 2 pi in a moment. So plug in 3 squared. So 9 radical 30 over 2. Okay. Plug in the lower bound, you get 0. Okay. So integrate this with respect to theta. So your surface area, you're going to have 9 radical 30 over 2 theta evaluated from 0 to 2 pi. So plug in the 2 pi, the 2's will cancel. So your surface area is going to be 2, I said the 2's cancel, so 9 pi radical 30. Okay. So surface area. That's how we do it. It's just a formula that I'm not going to derive for you. Okay. So I showed you where some of the other formulas come from, but I'm not going to take the time to do this. Okay. Because you did surface area in Calc 2. So in 2 dimensions. So now we're going to do it in 3. Area of a surface, you know, in a XYZ plane. All right. I have more examples of surface areas. So we're just going to kind of do a few more of these for tonight and then call it a night. So I'm going to go to the next page. You're going to remember what the formula is. I don't have the formula written on the next page, on the other pages. Okay. So your surface area under the radical 1 plus partial with respect to x squared, partial with respect to y squared. And you just have to just do the assessment. Are you going to do this in rectangular or do this in polar? You can't convert everything to polar, right? Just sometimes some of these problems will lend themselves better in polar. And when they do lend themselves better in polar, we like to jump on that opportunity. Okay? Polar conversions just make things easier for us. Example 2. So, okay, I need to give you a new screensaver there one of these days. Example 2, it's your textbook problem, number 8 in the textbook, okay? So number 8 in the textbook this is what it says. All right? And I'll tell you right now, so this is not going to be a polar conversion problem, is it? Okay, so you're definitely doing this in rectangular. So we want to find the surface area. I can't write this small with this marker, right? Okay, so it's kind of messy, but I just wrote the formula there again. So let's go ahead and get the surface area. Okay, so what about the bounds? Well, they're both given to you, and it's 0 to 1 and 0 to 1. So you just have to decide, after we set it up, you just have to decide if you want, yeah, I can choose the thinness of the pen. I could just hit buttons up there. I just wanted to put the formula in there thicker, but that was not a smart thing to do with all those partials. Okay, so 0 to 1, 0 to 1. So let's set up the integrand, and then let's figure out if we want dx, dy, or dy, dx, because it's not going to matter, right? So the integrand is going to be 1 plus, I need the partial with respect to x. So distribute the 2/3, 3/2, bring that around front, take one away. It's radical x, and I want to square that, okay? Then I need the partial with respect to y. When you distribute the 2/3, 2/3 y to the 3/2, when you take the partial of z with respect to y, you're gonna, the 3/2 comes around front, cancels with the 2/3, doesn't it? Take one away from the exponent, you get radical y. Don't forget you want to square that. And then dy dx or dx dy, it doesn't matter. Okay, so this one's just a toss-up, it just doesn't matter. All right, so we're going to integrate 0 to 1 and 0 to 1. And then under the radical, it's 1 plus x plus y, and this just doesn't matter. X first, y first, it's all the same. It doesn't matter, right? So integrate with respect to y first. Want to do that? So if you use u substitution, du is just going to be dy. So you're going to just u to the 1/2 power. So you're going to end up with 2/3 times your u quantity, which is under the radical, to the 3/2. And then that's going to be evaluated from 0 to 1. Okay, and then we'll do the x afterwards. Okay, and we integrated with respect to y, so you're going to plug the 1 in for the y. Plug in the upper bound. So when you plug in the upper bound, you're going to get 2/3. Plug in the upper bound for y, so you get 2 plus x. Okay. Minus, when you plug in the lower bound, you get 2/3. You plug in the lower bound 0, you get 1 plus x to the 3/2. Okay, so it's fundamental theorem of calculus, but I went ahead and split it up like that. All right. So, and then integrate each piece. So use substitution, but u is 2 plus x or 1 plus x, so du is just dx, so you're just integrating. So just be careful, right? So you got the 2/3. And then we want to integrate 3/2, so it's going to be times 2/5 times the quantity to the 5/2 for this one. Okay. Minus, you have 2/3 already. Okay. And then you're integrating this, so it's going to be times 2/5, 1 plus x to the 5/2 here. We value it from 0 to 1. Plug in the upper bound. So it's 4/15. Plug in the upper bound 1, so you get 3 to the 5/2 minus 4/15 times 2 to the 5/2. Plug in the lower bound, you get 4/15 times 2 to the 5/2 minus 4/15 times 1 to the 5/2. So we can combine those middle terms there. So 4/15 can come out of everything. So you have 3 to the 5/2 minus 2 times 2 to the 5/2 plus 1. And that can be simplified. We can simplify this right here by keeping the base and adding the exponents. So 4 over 15 factored out, 3 to the 5 halves minus keep the base and add the exponent, 2 to the 7 halves. Okay, and then plus 1. Okay, that's it. All right, that's it. All right, I have the correct answers written over here on a sheet of paper. So that is the correct answer for this. So that's it. And a lot of your surface area answers come out looking like that. Okay, so decimal approximations are always welcome for those kinds of problems. But when you see these on homework 4, homework 4 is not due for 3 weeks. So some of you might be getting on it. You might want to do, when you see it posed, you might want to do the center of mass and the surface area problems right off the bat to get them done. So if that's what you want to do, then you have examples here, but the answers come out looking like this usually. All right, 717, I think we got time to do one more. I got one more on the next page. One more surface area, there's your formula. One more surface area problem. All right. And then we'll pick up with all this next time. We're gonna hit triple integrals. We're gonna start looking at triple integrals. So, and then we have to do a UV substitution at the end of the chapter, and we have to do cylindrical and spherical, right? So double integrals and rectangular, and sometimes if you have circular regions, it's easier to do double integrals and polar. We like to see if we can do polar instead of rectangular with double integrals, okay? Wednesday, we're gonna learn triple integrals. We gotta work with triple integrals, okay? And then Wednesday, cylindrical and spherical, those are like, well, triple integrals. And if you wanna switch triple integrals to polar, okay? So triple integrals and polar, but they can't call it polar because you have triple integrals means you have 3 variables, but polar is just r and theta, isn't it? Okay. So cylindrical and spherical are like the equivalent of, so polar is to double integrals as cylindrical is to triple integrals. Okay. If you want a little, whatever you call that, little analogy thing. Okay. All right. Let's see if we can get a third example in before you guys go home for tonight. All right. This is totally frozen. Just won't. Okay. Let's see if we can get this one done. This is your book problem number 10. So in the book, you guys are supposed to be doing, you guys in the book are supposed to be doing 1, 3, 5, 7, 9. They're all find the surface area, find the surface area. Okay. So all of them are just find the surface area. Okay. So, so if you remember from the very first example we did, I like to start by getting z equals. Okay. So z squared, I'm going to just use a small marker on this. Okay. So z squared is 4 minus x squared minus y squared. So z is going to be plus or minus, well, I'm just going to put this because it's going to cancel out later. Okay, so I'm going to use this. That's what my z is. Okay, all right, so good so far? So lies above the line, the 1. Okay, so this means here, so you have x squared plus y squared plus z squared equals 4. And if it lies above the z equals 1 line, then we're going to substitute this in. Okay, so we're going to substitute in for z, we're going to substitute this in. Okay, so x squared plus y squared plus 1 squared equals 4. Subtract 1 from both sides. X squared plus y squared equals 3. Okay, so this is going to be our base. All right, this is going to be our base right here. All right, so that's our base that we're going to consider. And this is our z equation. All right, so let's set it up. So under the radical, 1 plus partial of z with respect to x, partial of z with respect to y. All right, so we set it up. We'll take care of the bounds in a moment. Let's do the partials. What's the partial of z with respect to x? Derivative of the outside times the derivative of the inside, right? All right, hang on. I copied it wrong again. Let me just erase it. Okay. So derivative, so it's chain rule. I'm taking the derivative of partial with respect to x. So it's 1/2 out front, okay, times 4 minus x squared minus y squared to the negative 1/2 times negative 2x. And all that's going to be squared. Okay. All right. And then we add to that the partial with respect to y, which is the same thing, right? So 1/2 4 minus x squared minus y squared to the negative 1/2 times negative 2y. We want to square that. Okay. dA at the end. All right. So let me simplify it. So we have what? We have 1 plus what is this going to be? Let's see, the 2's can't, you got to square it, right? The 2's cancel, so you're going to have x squared over, and then you're squaring the radical in the denominators, 4 plus x squared plus y squared. Okay, so 4 minus x squared minus y squared. All right, we okay on time? Minus x squared minus y squared, okay? Here you're going to have y squared over that same denominator. So, okay, so you have this. So, what do you see? What are we gonna do next? All right, you okay so far? So I took this and got my z equals so I can get my partial with respect to x, partial with respect to y. Okay, so partial with respect to x, partial with respect to, so the partial with respect to x, derivative with respect to x, right, is going to be 1/2 times the quantity to the negative 1/2 times the derivative with respect to x, negative 2x. I got to square that, okay? Partial with respect to y, so derivative of the outside times derivative of the inside. So the outside 1/2 quantity to the negative 1/2 times the derivative, this is a negative 2y, derivative with respect to y. I got to square all that. So when you square this, the 2's cancel. So you have negative x squared, you get x squared. And when you square the radical, because it's negative, drop it to the denominator, but when you square the denominator radical, the radical goes away. Okay, and then you follow suit and do the same thing here. So this is correct so far. All right, but do you see that we want to convert to polar? This is a polar problem. They don't tell you that in the book, right? This is number 10 in the book, okay? Now, the surface area problems are 1, 3, 5, 7, 9, so this is a harder one, okay? But we definitely want to convert to polar. Okay, so we want to convert to polar. So let's do the conversion to polar. All right, we'll come back and get the bounds, but what do we let x equal? All right, actually, before we convert to polar, let's do this. Let's combine like terms. So it's not even writing, okay? All right, so it's not even writing yet, okay? So let's do one more. Hang on. All right, I'm trying to write. Let me write again. Okay, so before we convert to polar, it might be easier to see the polar if we combine these two terms, okay? So let's just combine these two terms, all right? I'll just do a different color here. So let's combine these two terms right here. All right, let's combine them. All right, so we have 1 plus, keep the denominator, so 4 minus x squared minus y squared. Keep the denominator, combine the numerator, so x squared plus y squared in the numerator. Okay, all right, and so now let's convert to polar. Okay, so let's convert this to polar. All right, so when you do the conversion to polar, under the radical, you have 1 plus, okay, the numerator is r squared. X squared plus y squared is r squared. The denominator is 4 minus r squared, because you can factor out the radical. I mean, you can factor out the negative. Okay. dA is r, dr, d theta. That's what it is. Okay, so r dr d theta. All right. And then what? The bounds. What are the bounds out front? Well, here's my circle. So the radius bounds are going to be from 0 to radical 3. All right, because the radius squared is 3, so the radius is radical 3. And then we're dealing with the whole disk. Doesn't give you any restrictions on it, so 0 to 2 pi for the outside bounds. All right, so questions there. It's kind of quiet over there. You guys still out there? Yeah, it says you're still here. Thank you. Okay. So I would, how are we going to do this here? Get a common denominator in there. Okay, let's get a common denominator. Okay, so your outside bounds are 0 to 2 pi. Your inside bounds are 0 to radical 3. This is going to be 4 minus r squared. 4 minus r squared over 4 minus r squared plus r squared over 4 minus r squared, right? R dr d theta. Okay, so the r squareds in the numerator cancel. So 0 to 2 pi, 0 to radical 3. Under the radical, you have 4 over 4 minus r squared. We want to integrate that. So how do we integrate that? U sub can be done, yes. But before we do the U sub, let me rewrite this. Let me simplify this more. This is not going to fit on this page. So the numerator, square root of 4 is 2, right? Can I do that? In the denominator, I have the radical 4 minus r squared. Okay. All right. So the denominator is not a perfect square. The numerator is. Okay. Then I got the r dr d theta going on, but I'm going to take this r and put it here. And there's my dr d theta. Okay. So the square root of 4 is 2. The denominator is radical 4 minus r squared. And I'm putting that r into the numerator here. Okay. All right. So yes. And so I was asking, so it was a private message here that says, can U sub be done? Yes. So we're going to let U equal 4 minus r squared under the inner part of the composite function. So du is going to be a negative 2r dr. Okay. So that's going to cancel with the numerator and pull out a negative. Okay. So we need to go on to the next page. You know what? Time is up though. So how about we pick up here next time, right at this spot. Time is up. I'll write it a little bit neater up to this point and we'll talk through it. We'll pick it up. I'll write it neater though, up to this point, and we will continue right from here on next time. Okay. Well, so it lies above z equals 1. So you just substitute it in, and that is going to be above z equals 1. Okay, so when you see these problems in the odds, That's how it's going to work. Lies above z equals 1. So you just substitute it in, and you're going to take the disk up, but you plugged it in. So, and it's going to work. Okay. To be continued. We're not leaving this one. We're going to come back to it and continue with it on Wednesday. So, but in the meantime, center a mass. Take a look at them in the book. I mean, I just do one problem from between now and Wednesday to get the concept in your head. And surface area, do a problem or two, get it in your head. Okay. I'm going to stop the screen share. I'll stay after if you want me to stay after, but we put enough late nights in. So